Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to talk about percent ionization of acids, okay? And we're going to do a strong acid versus a weak acid as far as calculating the percent of ionization. So let's begin with something like hydrochloric acid. Let's kind of do kind of like an apples to apples comparison. Let's go ahead and do 0.25 molar of HCl, okay? Now, this is a strong acid, so I want to label that as a strong acid. And what we're going to do is we're going to start out with a good equation for hydrochloric acid, and we are going to use a single arrow to represent that it's going to transfer completely over into its ions, okay? And of course, we're going to use a BCA to show this. And if we start with a 0.25 molar, remember we don't really worry about water in this, okay? It doesn't have an effect. So we know that this is going to go down 0.25. There's going to have to be anything left. So this can go up 0.25. This can go up 0.25. So these are the values that we get when we finish the BCA chart that we've learned in the previous videos. And we want to figure out, well, what is the percent ionization, okay? Well, the part that we're interested in is how many protons are created at the end, so after, okay, versus what we started with as far as an acid. So how much of this, was created from this. So our concentration, if we're calculating our percent ionization, our concentration of protons at the end is 0.25, okay? And that's out of how much we started with. So where it says HA, that's just our acid as starts with a hydrogen, and it always has some type of negative ion, which we call an anion. So in this case, it's chlorine here. Okay, so HCl is kind of what we're talking about here. So this is going to be 0.25 times 100. Well, 0.25 divided by 0.25 is just 1 times 100. Well, we have 100% ionization with strong acids, and that's because of the full shift to the right, okay, signified by the single arrow, okay? Well, a weak acid is going to look a little bit different. It's not going to have 100% ionization. So let's take a look at a situation where we have kind of like a beaker, and we're going to keep the molarities the same. It's 0.25 molar hydrofluoric acid, okay? Well, once again, it always starts with a good equation. So we're going to start out with our weak acid, and we're going to put it with water, but instead of a single arrow, it's going to be an equilibrium arrow where the proton is transferred over to create hydronium and fluoride ions. Of course, we're going to use an ICE chart because this is in equilibrium. There's going to be a balance of both the reactants and products. It's not going to be the full shift that we get with the strong acid. Our weak acids only shift over a portion, okay? So I'm going to put in the 0.25 just like I did last time, set it up exactly the same way, okay? Now, we know this is going to shift to the left a little bit, so this is going to be consumed. This is going to go up X. This is going to go up X because of the 1-to-1-to-1 coefficients, the stoichiometry ratio. And this is going to be 0.25 minus X. This is going to be X, and this is going to be X. And if I'm going too fast here, it's on purpose. And if you want further details on this, this is in a previous video on how I did all these calculations, okay? But we're going to go in, we're going to look up the Ka value, and it ends up being 6.8 times 10 to the negative 4. Well, times 10 to the negative 4 with a concentration of 0.25, I feel really good at using the approximation method. And what that means is that this shift is so small that's going to the right that 0.25 minus a very, 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 very small number is still going to be right around 0.25. And by doing the approximation method, I eliminate the requirement of using the quadratic equation, which I'm very thankful for. So Ka is going to be equal to the hydronium ions times the fluoride ions divided by the hydrofluoric acid. And I just plug everything in. This is equal to X. This is equal to X. And this is equal to 0.25. Okay. and that's all equal to 6.8 times 10 to the negative 4, okay? So I'm doing some cross multiplication. X squared is equal to 0.25 times 6.8 times 10 to the negative 4. I'm going to multiply those two numbers and then take the square root, and the square root ends up, or x is ending up being equal to 0.013, okay? Now that 0.013 is the part that I'm interested in, because I'm interested in the hydronium ions and how many hydronium ions were created from the weak acid. And I'm just going to plug them back into this equation for percent ionization. So for percent ionization, the amount of hydronium that I got, 0.013, out of what I started with, 0.25 times 100. And if I take 0.013 and divide it by 0.25 times 100, I get a percent ionization of only 5.22%, okay, which is far less than the 100% that I got with the strong acid. So remember, strong acids, 100% ionization, okay? Whatever you start with the acid, you're going to get that with hydronium ions and the negative ions. Where a weak acid, it's just going to be a partial shift, okay? You're going to still have a lot of HF in here, okay? About 95%, but about 5% is going to be the hydronium ions and fluoride ions. So I hope this content was helpful. If you thought it was, please give it a like and subscribe. When you add that comment, it does push this information out to other students that are interested in learning chemistry.